Hey guys, F Train here. It's Thursday and it's May, what is it, May 21st. I know that because my wife's birthday is in 2 days. I can't forget that. Um, anyway, it's been like over 2 months since I've seen you guys in person. It's been a very long time. And you probably haven't really seen me much on video since you've been seeing yourselves. Which you guys did an awesome job on those video review sessions. Hopefully those of you guys who took the APA exam, that it went well. And anyway, this is going to be hopefully a pretty interesting lesson. The last lesson I gave you a video to watch about special relativity. I don't There's nothing that I've seen that I really like as much for general relativity, so I'm gonna do it myself. Anyway, so here is a lesson about general relativity. So first of all, we have this do now here. What are some other effects of special relativity besides time dilation? So hopefully you might want to pause and think about that. And now you might be thinking, you might have written down in your notebook non-simultaneity, length contraction, things of that nature. Okay. All right. So today we are going to, like I said, talk about general relativity. Also an Einstein thing, Einstein's special relativity. I think he came up with that in the, I want to say 1904, don't quote me, but then I think general relativity was more like 1915. In fact, they just celebrated the 100th anniversary a while ago. And it was actually not until 1919 that it was confirmed. And we'll talk about that right now. And this was an article that was in the New York Times in 1919, and I'll let you read that. And what question does this raise? I love the word agog, by the way. Man of science, more or less agog over the results of eclipse observations. So what question? So the question we're going to talk about today is why did an eclipse change the position of the stars? As you read in that article, the known position of stars changed during an eclipse. And this leads us to the theory of general relativity. Again, Einstein's theory of general relativity. There's the general. Okay, so imagine throwing a ball horizontally inside a spaceship in outer space. Okay, so you're in outer space, you're just floating in outer space in a spaceship. Okay, no forces, no thrusters, anything like that, and you throw a ball horizontally. Now, but as soon as the ball leaves your hand, the spaceship begins to accelerate upward. How would the ball appear to move to an outside observer? So what I'm going to do is I'm going to give you a little diagram, and then you can kind of copy it and draw what you think it would look like to an outside observer. Okay, so here's my spaceship. Okay, there's my baseball. The baseball leaves my hand at that instant there. And then as soon as it leaves my hand, the spaceship starts to move upward. Okay, so let's say, a little bit later, the spaceship is now up there. So what would the path of the ball look like to an outside observer? So maybe you can draw that yourself, okay? Basically, the answer is to an outside observer, once that, once that ball leaves your hand, there's no forces acting on it, right? Because you're in the middle of outer space. And so therefore, even though the spaceship moves upward, I guess you'd have to assume there's no air in the spaceship, because otherwise you might have some force from the air molecules pushing on the ball. But if there's no forces, then what's going to happen is that the ball is just going to move in a straight line. Okay, but how would the ball appear to move to an observer inside the ship? Okay, so think about you just threw this ball, and then all of a sudden the spaceship starts to move upward. So maybe, take the same spaceship and draw the path of the ball inside the ship. To an observer that's inside the ship. And hopefully you would realize that according to an observer inside the ship, the ball is actually going to appear to drop. And it's not really that the ball is dropping as much as the floor is kind of coming up, but relative to the person who threw it, relative to the floor, the ball is dropping. Okay. And Einstein called this the equivalence principle. And he said that observers cannot distinguish locally between inertial forces due to acceleration and uniform gravitational forces due to the presence of a massive body. So in other words, if you had this, this is an elevator now, or let's say this is your spaceship. So if you were on the Earth and you drop this apple, or if you threw the ball or whatever, we know the path that ball or that apple is going to take. It's going to fall down, okay? Or the ball is going to, make a curved, arced path, okay? But in this spaceship that's accelerating upward, the ball would behave exactly the way it does on Earth. And Einstein tells that you can't tell the difference. So if this spaceship was accelerating upward at 9.8 meters per second squared, it would feel exactly like if you were on Earth. Okay. Now, how would this experiment differ for a horizontal light ray instead? So instead of, throwing a ball horizontally, what if you were to, take a laser pointer or something like that? And the answer is that it would not. It wouldn't be any different. Now, it would be different in the sense that because the light ray is moving much more quickly, it's not going to, it's not going to sort of drop as much. In other words, the path is going to be a lot straighter than the ball because the ball's going a lot more slowly. But I mean, if your spaceship was wide enough, you would, and let's say you could throw your ball at the speed of light, then the ball and the light would behave exactly the same. Okay. And so, according then to the theory of special relativity, what causes space and time to distort? I should have said it like this. According to the theory of special relativity, what causes space and time to distort or change? And we remember from our last lesson that is the relative motion of the observer. So, if you have somebody, an object moving, a spaceship moving, time appears to move more slowly to an observer on the Earth, okay? But Einstein concluded that mass also causes distortions in space-time. And the way he put it is that mass tells space-time how to curve, and then the curvature of space-time, which is gravity, tells mass how to accelerate. So objects that are subject to gravity are simply following the shortest path on the curved surface of space-time. And this shortest path is known as a geodesic. Now, you're familiar with a geodesic, even if you don't know you are. If you've ever flown on an airplane or seen the route maps of airplanes, okay? So let's say you're here in Chicago, and you want to end up over here, looks like somewhere in, Iraq or something like that. I don't know, somewhere along the Persian Gulf, it looks like, okay? So really that point is pretty much due east. Or let's say you wanted to go from Chicago to Japan. Japan is pretty much due west of Chicago, okay? However, you wouldn't necessarily want to fly your plane due west to get to Japan or due east to get to Iraq because that is not the shortest distance. If you go up and over the Earth, okay, over the, sort of close to the North Pole, it's going to be a lot faster. In fact, it wasn't until maybe like 20 years ago or so that they opened up air routes so that you can actually fly kind of over Russia and get to Japan and Hong Kong and places like that a lot more quickly. Okay. So that's a geodesic. So if you look at this now, here is my, I have a star here. Okay. And light is coming out from that star in all different directions. Okay. Now, you can imagine though that only one of those light rays is actually going to hit your eyeball on the Earth down here. Okay. And so the light ray that hits your eye is this yellow light ray. But because this light ray might be passing near the sun has curved space-time, okay? And so the shortest distance along the path of space-time from that star to your eyeball is actually going to be this curved path here, okay? Sort of similar to what we were talking about with the airplane routes. Now, because of that, you'll notice that since this yellow ray is coming at this angle, if you were to look up, you're not going to realize that this ray actually curved, along the way. You're going to assume that it came from up there, okay? And so that star is going to actually appear to be up there. So it's going to appear to move. Now, this is I'm sure a greatly exaggerated picture. However, this is exactly what happened on that day in 1919 when they confirmed special or general relativity. Okay, and so we are going to talk about 6 confirmations of general relativity. Okay, so general relativity is a fact. Okay, it's not a it's called the theory of general relativity, but it's been proven many times in many different ways. And some of these ways are, number one, the perihelion precession of Mercury. Now, you guys remember the term precession from last semester, and so this is the orbit of Mercury around the sun. Again, it's the elliptical nature of that orbit is pretty much exaggerated. But remember, perihelion is the closest approach of Mercury to the sun. Okay, and you can see that over the years, that closest point actually moves. Okay, it precesses, much like the Earth's. Remember, we talked about the celestial North Pole precesses, and over a period of like 26,000 years, it will move through all the constellations and then back to, in this case, it's, Polaris. It'll, in 26,000 years, it'll precess all the way around and come back to Polaris. But in the meantime, it'll move through all different constellations, okay? Mercury's perihelion precesses about 574 seconds of arc per century. Now, that's a very, very small amount, okay? You can calculate how long it would take to precess once, but it's very, very slow. But this is about 43 seconds greater than can be predicted by Newtonian mechanics. And that precession due to Newtonian mechanics is mostly due to the pull of other planets and things like that causes the orbit to precess. Okay, so and it turns out that if you throw in the equations of general relativity, this exactly makes up for that extra 43 um, seconds of arc. Okay. Another confirmation is the one we already talked about, the deflection of starlight. And so Einstein in 1915 came up with this theory. Turned out that it was about 4 years later, I guess that was like in November of 1919, when there was a first total solar eclipse. And the thing about a total solar eclipse is that you can actually see stars in the daytime. Okay. And so you can see stars near the sun. Okay. And those stars, if you look at, those stars are mapped and we know exactly where those stars are. However, on that day during the eclipse, those stars shifted. Now, I don't know if you can see, let's see if I can, I don't know if I can make that bigger, but um, they shifted very, very slightly, okay, very slightly, but enough that they can be calculated the amount they were shifted, and it agreed with general relativity. Okay, here's another, and by the way, this was a guy named Arthur Eddington in 1919, who's the astronomer that went out on this voyage to to observe this total solar eclipse. Here's another picture of this happening. You've got the actual starlight here. When it hits the Earth, it bends, and so therefore the star appears to be over here. Okay, it appears to shift slightly in its location. Okay, another confirmation of general relativity is something called gravitational lensing. Now, this was first observed back in 1979, and it's pretty cool, actually. A quasar is a super, super distant galaxy. We're talking like billions of light years away. It's basically a galaxy where has a massive, supermassive black hole in the center, and all this materials falling into it. So as it falls in, it's super bright. So quasars can be seen literally like billions of light years away. They're some of the brightest objects that we know of. Now, what happens though is, let's say this quasar is the light is going off in all directions. Well, what's going to happen is that the light that goes up like this is going to bend around, let's say, a massive galaxy that's in between us and that quasar, and it's going to go up and then it's going to bend down. Again, this is exaggerated, but then a ray that's coming down here is going to bend up. And so what's going to happen is then you actually see two images of this quasar. Now, in 3 dimensions, you can actually imagine maybe you even see a ring, okay? But sometimes for some reason you only see, so this is an example of these twin quasars that are observed. Now, how do we know they're the same? Well, you can analyze the spectrum. And so you can tell you're actually looking at the same object. Okay. Another confirmation of general relativity is general relativistic time dilation. Okay. And what does that mean? That means that just like we know that when a clock is moving fast, it ticks slower. Well, a clock in a more stronger gravitational field also ticks slower. So imagine if you had a clock at the base of a mountain, it's closer to the center of the Earth, it's going to tick more slowly than a clock that is at the top of a mountain where gravity is less strong. And using atomic clocks, which can be measured to a precision of billionths of a second, you can actually measure this quite accurately. Okay. Gravitational redshift. The idea here is that when light leaves, let's say a star like the sun or whatever, okay, as it gets further and further away from the sun, gravity is weaker and weaker. And so what happens is that you have a slight depending upon how far you are away from that star, you have a slight lengthening of the wave. So redshift, lengthening wave means redshift. Okay. So the wavelength of light shifts toward the red end of the spectrum as it comes out of a gravitational well. And then lastly, this is probably one of the coolest ones, is gravity waves. Okay. Gravity waves are ripples in space-time arising from massive explosions. And rather than go into this a lot, I actually have a video that I'm going to attach to this. But basically, there's this thing called LIGO, okay? And it's essentially an L-shaped detector that has these lasers. And as a gravity wave moves through the Earth, it actually causes the move to stretch and, get compressed and stretch in both directions. And so this very long laser beam will change very, very slightly in length, but it can be measured, okay? It only changes like 10 to the minus 19th meters, which is very small, but it's a very precise instrument. So watch the video, it's very interesting. And this happened about 5 years ago, actually. I remember the day it happened. It was like the beginning of the school year, and and it was probably one of the biggest things that happened until a couple years ago, when of course we saw that picture of a black hole. And so we actually, we spent pretty much the whole day in class, astronomy class at least, talking about that, maybe even in the physics classes too. Okay, so anyway, I'm gonna attach that video. General relativity. So if you want, you can discuss with your homies how do we know that general relativity is a thing. Okay, and that's going to be part of your homework as well. All right, so I hope you're doing great. I hope you have a great rest of your week, a great weekend, and I will talk to you guys soon.